Take a second and just imagine this. Your body is a bustling city of biomolecules. Enzymes are twisting, proteins are folding, and reactions, that spark life itself. But what if the secret of understanding these processes lay not in the classical biology, but in quantum physics? Could the same principle that govern atoms and molecules also shape how enzymes catalyze their reaction, or maybe how drugs interact with their targets, or even how signals travel through neurons? This might sound like something out of space, but it's cutting-edge reality, and few people understand it better than our guest today, Professor Mikhail Lemeshko.
You have some very complex systems, some very complex material, or some, in biology also, some very complex system. What is the simplest possible model that would describe the behavior or some key features of the behavior of the system?
His groundbreaking work on Angulons, that's a new kind of quasiparticle, is helping scientists to describe how rotating molecules interact with their environment. Something that could be crucial for understanding biomolecular behavior at the quantum level.
Called chirality-induced spin selectivity effect. So what is it? Like CISS, so chirality-induced spin selectivity.
Get ready for a mind-expanding conversation with Professor Mikhail Lemeshko, physicist, professor, YouTuber, and the scientist showing us that you have never experienced physics like this before. Have fun and enjoy our conversation.
Daily dose of honest science.
Hello guys and welcome back to Daily Dose of Honest Science, your science-based biomedical science podcast that you can hear on any podcast. I'm your host, Dr. Chandni Kumar, and today's episode, I went really out of my comfort zone. It's called Daily Dose of Honest Science, not biomedical science, so we need to also have our other colleagues from other disciplines. Today's guest is someone who explores a hidden layer of reality, one that influences not the physics, but potentially maybe also biology and chemistry as well. Professor Mikhail Lemeshko is a theoretical physicist whose work on quantum many-body systems helps to understand how groups of atoms and molecules behave in ways we wouldn't expect from studying just one particle alone. Well, now you think, why should this matter to those of us who are thinking about living systems or medicine? Well, nature operates at the molecular level, and quantum effects can influence critical processes from how proteins fold to how chemical reactions occur inside our cells. So, by studying how quantum interactions emerge in many particle systems, Professor Lemeshko's work or research could provide insights into biomolecular dynamics, drug interactions, and even how we manipulate molecules for medical applications. With an impressive career spanning in Harvard, the Max Planck Society, and the Institute of Science and Technology in Austria, and prestigious awards like the ERC Grant, Starting Grant, and the Ludwig Boltzmann Prize, Professor Lemeshko is at the forefront of this very exciting field. Beyond his groundbreaking research, Professor Lemeshko is also very passionate about science communication, sharing the wonders of quantum physics with a wider audience through his amazing YouTube channel. A big applause and a warm welcome to our show. Hello, Professor Lemeshko. Thanks for your time. Hi, Misha.
Hi, Shani. Thanks a lot for the invitation, and I'm not going to comment on this introduction because it was a little too much. I wanted to say a little too much. I'm looking forward to the conversation with you,
Okay.
And to learning a bit about biology as well.
On social media and YouTube, you always have to exaggerate, right? So, otherwise, how will you get the attention of the people? But I think you're doing a really great job. So it's really cool to have you as a physicist here. And the first section in my podcast is always to get to know the guest a bit more. So You're a theoretical physicist, and I would like to know, how do you actually got into science, and why especially physics?
All right. So I was born in the Soviet Union, actually, it's true, and it was pretty strong. As a like all natural science disciplines were pretty strong, and probably at the expense of humanities. So I'm not saying I would be like doing humanities, but um, there were not that many options actually if you are a person who wants to do something intellectual in like former Soviet Union, back in the Soviet Union, but then like after the Soviet Union collapsed. There were not that many options because all humanities were kind of destroyed by the propaganda kind of machine, in the
Mhm.
sense that you couldn't study like history. You had to study like history of Marxism, Leninism. You couldn't
Mm.
study philosophy. It would be some like dialectical materialism, and you would be like studying Marx and Engels and whoever, and Lenin. And there were actually a lot of people who, I'm not one of them, but I know personally people who are like basically at the Nobel Prize level, being physicists, and they admit that if it were possible to do like philosophy in the Soviet Union, they would have done that, or
Mm.
like history, but all these options were closed for people who didn't want to deal with like deal with kind of like communist party and their agenda, and therefore basically all smart people went into natural sciences. So it was
Mm.
like physics, chemistry. I mean, biology is also, unfortunately, biology was also killed at some point, like when genetics was developed. There was I don't know if you heard, like there was this case of Lysenko, a guy who was basically uh, telling Stalin that genetics is like too idealistic to be true. We can talk about it later, but basically all geneticists or many geneticists in Soviet Union were killed, and that stopped Soviet biology a lot. So biology is not as strong traditionally there as like physics, math, chemistry. And what I mean is like naturally it was like one of these ways. If you want to do something like intellectual, you do one of these disciplines. Then why physics? I mean, I also partially, I'm not going to lie, I had some physicists in my family. And it was also like, I mean, chemistry would also be an option, or math, or some kind of programming related things like applied math. But yeah, I mean, I liked physics. I was also like immersed through some relatives at some point, and yeah, but I would have done something like on the side of exact or natural sciences anyway. So
Mm. Wow. I didn't expect this kind of background, so thanks for sharing.
it's
Uh,
too much talking. We
no,
need
no,
to fill
no.
2 hours, no?
It's I, you know, I wouldn't imagine politics so to be down the route, so shaping your path in your
Oh,
life.
indirectly, it's not like my path, but it was like I just mean why, like it was very natural to do some like natural sciences
Mm.
in post-Soviet Russia for someone who wants to do something,
Mm.
um, intellectual. And
Mm. Mm. And maybe just very quickly, now many things have changed. There's not Soviet Union anymore. We have Russia. Um, do you see a change there? Do you see a change, or is it still like, let's say, killed and only specific topics are researched on?
well, I also don't want to, like, the world is not black and white. And like, for example, uh, natural sciences in the Soviet Union, they were extremely good, and the world is still full of theoretical physicists that came out of the Soviet school, and they work at places like Harvard, MIT, whatever. And I'm a part of this community indirectly. I studied there, and that gave me also a lot of opportunities. So these things were very strong, at expense maybe of like humanities.
Mhm.
But then these days, after long time ago, after the collapse of the Soviet Union, things kind of fell apart, and it was Russia of the 90s was a very kind of dark place. A lot of people immigrated, so basically all or most people who were really serious scientists immigrated in the 90s. Then like they continue to immigrate until now, and like war in Ukraine and so on. Of course,
Mhm.
it also squeezed the last people out of Russia.
Mhm.
And now, like, I mean, for a long time, it's not like there is not much to talk about there. Like about scientists working in Russia, there is not much. Like education is still okay, but there is a huge diaspora. So there is a lot of like Russian scientists they determine a lot of like world's physics, chemistry, math, and biology. Actually, there are like I know there is like Kunin. I don't know if you know this guy Kunin, who was like a bioinformatician. He's one of the most cited scientists, I think, in the world, even like not only biologists.
Okay.
In the works in the US. But anyway, um, so there is a huge diaspora that is kind of keeping the traditions of the collapsed Soviet kind of science.
Ah, okay. That's very interesting to know. Um, and you are working particularly as a theoretical physicist in the world of quantum dynamics, let's say. And I would like to, there's this famous show called The Big Bang Theory. I guess
Sure.
many people have seen it. Maybe you can give also a bit how accurate it is, but I would like to cite Sheldon Cooper, who said, in classic physics, reality is what you observe. In quantum physics, reality is what you measure. And in biology, they are still looking at frogs. So
Well, even I know that it's not true about biology, but whatever. Okay.
so so you don't agree with Sheldon Cooper, so you would say
Well,
it's a
okay.
bit.
I can I could give like a 2 hour lecture about this sentence about what well, like my take on it. Two things, right? So first, like how accurate Big Bang Theory is. Well, it is pretty accurate, of course. The world of physicists, of like nerds, is full of not neurotypical characters. Like Sheldon Cooper, of course, like every single character trait that Sheldon has or whoever, like Howard Wolowitz has, I have seen somewhere. Probably it's hard to find the person that would like combine all of them in one, like Sheldon. But it's all like nothing surprises me. On the other hand, okay, like there will be three things. So second thing is that there are theoretical physicists doing like particle physics, like string theory and these type of things. I'm not doing that. I belong to a completely different community that
Mhm,
studies physics around us. So I can also like I recorded, I don't know, like many videos on that topic that there are two types of physicists. There are physicists who are like working in a kind of reductionist way that are building large colliders, try to do like smaller and smaller particles, higher energies. But there are and in that field you have experiments that are like sometimes taking 40 years long, right?
mhm,
And most physicists do not work on that way. So that might be surprising to many people because what we hear in like popular sources like newspapers is all like string theory, like large hadron collider, I don't know, like superluminal neutrinos and stuff like that. But most physicists don't do that. So most physicists don't work 50 years for a new collider to be built. Most physicists study like properties of materials, like they develop new techniques to study, I don't know, to make your iPhone better, whatever. Potentially there are a
yeah,
lot of fundamentally interesting questions on the way. So there is a lot of fundamental physics in physics around us and the properties of like many interacting electrons and so on. And there you talk to experimentalists literally daily. So
mm,
we talk to experimentalists all the time. We have like many papers, like I know half of our papers at least are with experimentalists, and we
yes, yeah,
talk to them. And so it's not like you wait and then there's collider. Do they find Higgs boson or not?
mm,
So this is second. Uh, Third, about counting frogs.
yeah,
So many physicists have this tendency to be a little bit like arrogant
oh,
and like all this Rutherford who discovered atomic nucleus
yes, yeah,
got Nobel Prize in chemistry actually back then, but he used to say that all sciences are either physics or stamp collection, basically. So meaning that either you like try to understand things and then it's somewhat physics, some sort of physics, or stamp collection, like looking at frogs and doing like systematics of butterflies you find in the jungle, right? Uh, so this is definitely not true. And well, from my perspective, like you tell me, I'm looking forward to your view on that. I think it's a huge mistake that many physicists make, that they come to another field, like be it linguistics, biology, sociology, economics, and say like, okay, you guys are stupid. You don't even know like how to solve like what are differential equations. I'm going to teach you like how you study things, and like, and many people kind of got burned thinking that way because every science, excuse me, every science has its way of like studying the world. Every science has its approach to the ratio between like theory and experiment, its approach to like what you count like as like demonstrated or not, like what's enough to like show that the phenomenon exists and so on. Every science has its own language to talk about the problems, and one needs to learn it first. And like the best is of course to work like if you go to biology as a physicist, to like find the strongest biologists you can and like learn from them, right? And not be arrogant. So I, of course, don't agree with this like counting frogs.
Yeah, I completely agree. And for me, it's always interesting when I work in a project. I always try to actually get other disciplines in, because usually we are limited at a certain point and we cannot go further if we don't have the expert from another field. So just as an example, when you study something that has to do with chemistry, it makes sense that you also have chemists on board. If you study something like biophysics, is something that is kind of important. If you want to know the kinetics of an enzyme or something, it already goes into the direction of physics. So it makes sense to have someone who is specialized in that field, and therefore it makes totally sense. But don't worry, there are also arrogant people in the biology field.
Oh, I know. You don't need to tell me.
So it's mutually that people are saying our field is better than yours. So
Yeah, I mean, there are biologists who believe that, for example, like science is linear. So like 18th century was like, or what, like 19th century was like century of chemistry, 20th century was century of physics, now it's like century of biology, and that like science is just basically like you close one field. Like, I mean, you know.
Yeah, but that's not totally true. So we have
It's
a
all
lot.
non-linear. It's more complicated than black and white. I mean,
Yes, yeah, totally. I totally agree. And right now, you're a professor in Austria. So can you explain to the audience what are you actually doing, and maybe elaborate on how long have you been doing this now?
you mean scientifically or?
No, I mean being a professor and having your own group.
Okay, so it's a good question. Like, what are professors actually doing? Like, how my day looks like? Well, as a professor, I'm leading a research group, and so I've been doing it since 2014, so over 10 years now. And
Congratulations.
yeah, thank you. And my group consists of like usually approximately 10 people. These are like PhD students, postdocs. We have sometimes master students, sometimes interns. Well, usually we have someone on short kind of term fellowships. And what we do, so what I do is as a professor is leading the group. So of course there are many components. It's like not clear, not clear, not clearly defined what I have been, what I have to be doing every day. In a sense, there are some duties. Of course, like I have a little bit of teaching. I have a little bit of like a little bit like of committees, like some administration. So we participate in like hiring of like other professors, of like some other committees. And in terms of group leadership, so my job is to make the group produce science, right? And so then it can vary. So like what people do usually. So some professors, well, very few professors actually have time to work themselves on problems just quietly, because it's like you don't have time to focus really, without being distracted. Especially in experiment, it is very rare. So sometimes in the beginning, so I'm not doing experiments, but like sometimes in the beginning you do some experiments, and then you kind of leave the lab and just kind of provide the big picture for the group. And in theory, I was also like continued to work on my own as well, along with like giving projects to my group members first, like I don't know, maybe 5 years, and then later, like at the moment, I'm rarely doing much work like on my own, like what I mean, like derivations or writing programs or whatever. But the work I'm doing, so scientific work I'm doing, is discussing science with my people. So it is always like we have a group meeting, for example, and we discuss, okay, what is that we need to do next, for example, or what problems do people face, like how can we solve it. And usually So ideally, so how I see kind of leadership is like you should be doing only things that only you can do, right? So for example, I try to hire people that are much better than me in some particular aspect. So for example, like I'm sure my postdocs and my like many of my students are much better than me, like in programming, in even in some like, so I hire postdocs that bring some expertise that I don't have, that are much better, like know some area of physics much better, right? But what I try to provide is what they cannot provide. So, for example, the big picture. So, I would be like, I know, I would go to a conference, meet someone, and say, okay, like, look, like this professor told me, like there are like these experiments ongoing. Okay, like let's look into that, right?
Mhm.
And they don't have that inside. Or like, for example, at the group meeting, sometimes like 20 seconds of my contribution is enough to change everything. Like they're discussing, they're stuck, and they would be like, okay, have you looked at that paper that I've seen as a PhD student like 20 years ago?
Mhm.
And they'll be like, oh, okay, we never look. And, they solve the problem, right? And all these like little things like shaping the group
Mhm.
work on the daily basis. So basically, well, it's a lot of talking actually, and a lot of like, things that you cannot formalize, like little things that you tell people, you hear from people, oh, have you talked to this one, to this person, or why don't you go to this conference and like learn from them, or like that keeps the group running actually.
Mhm. And funding wise, it's also a bit different, I guess, right? So you are also, your main output are papers, I guess, and then you're measured by this as well. And the question is, since you are doing theoretic physics, is and you're not doing experiments on your own, how does this look like? Is it you read papers and make theories, or how can I imagine this? So what is your um,
Yeah, so usually we do science that is quite relevant to experiments. So we try to, although it can go both ways. So it could be experimental data that needs to be explained. And for example, here we have some experimentalists that like come knock on our door and like, okay, I measured something, I have no idea what's going on. Could you help us? And then we brainstorm and we try to explain it.
okay.
Sometimes we have ideas. Okay, it would be cool to measure this effect, like some new physics, some like
Mhm.
new type of state of matter, whatever, like some new quantum effect,
Mhm.
and we try to find a way how it could be done experimentally. So we try to propose it and then go to experimentalists and suggest how to do it.
Mhm.
But sometimes we also try to push the theory forward, theory per se.
Mhm.
So try to develop new theoretical techniques to understand some theoretical models better, for example, that are also relevant to experiments. But in some papers, it's not the goal. The goal is also like to develop some kind of new language to describe some new material, for example. And we say like, okay, there is this model. We studied this model has this and this and this property, and then later at a later stage we can also go to experimentalists, and like next paper for example will be about concrete experimental application.
Mm. Do you have an example of this recently
Yeah,
produced?
so for example, so I also recorded a video about it recently. So one of our projects deals with so-called hybrid lead halide perovskites. So it's a field that is quite broad in chemistry. So these are crystals. So imagine like it's a crystal and there are molecules rotating in this crystal.
Mhm.
And people discovered that these crystals are extremely good for solar cell applications. So you can make a good solar cell out of it.
Mm.
People do not understand why.
Okay.
So chemists do not understand why. It is very surprising because the solar cells that you have, usually like normal solar cells, are made from very pure materials like gallium arsenide, some monocrystals. So they are very pure, hard to produce. They need to be like perfect. And
Mhm.
now you take this crystal, which is like hybrid organic and organic. So organic materials are like dirty. As a biologist, like
Mhm.
what kind of solar cell can you make of like some protein? I mean, it's not like protein, but like
Yeah.
it's kind of halfway there.
Yeah.
Like it's a dirty material. This crystal, like you have these molecules rotating, you look how it behaves, these molecules distort everything, the whole lattice moves.
Mhm.
So this material is not even like a real kind of crystal. It's kind of in between crystals and liquids in some sense,
Oh.
because it's very soft, very unharmonic. Like why the hell does it work so well for solar cells? It is unexpected. So it works about as well as like very pure materials, but it's much cheaper, much easier to produce, like chemically tunable and so on.
Mhm.
Now, what chemists do, they largely, no offense to chemists, but basically a lot of this field, and the field is huge. So I think like several thousand papers per year are produced on these materials.
Okay.
And what they largely do, or have been doing a lot, is they mix stuff, they synthesize new material, and they measure the properties in the hope to get a new material which is going to be even better for solar cells or for some other applications.
Mm.
And they like largely, I mean, it happens also in some fields of chemistry. It happens that people like put a PhD student and they're like, we're going to get a lot of hate comments, but it's good for like YouTube algorithm. But I mean, okay, my take on it, you can cancel me if you want, whatever. So, but in some fields of chemistry, what they do, they put a PhD student. Okay, you have like 4 years, mix, measure, and like you get something, and like, okay, you can graduate. Not all chemists, like hashtag not all chemists, but whatever.
Too easy.
And I talked to some people even in this community, and like, okay, fine. Like I'm like a fundamental physicist. I'm interested in like some like fundamental properties of materials, for example, of these materials. It doesn't matter. You don't need to share my opinion, like my passion to like fundamental questions. But if you want to solve the purely applied problem, don't you want to understand what's going on, right? Because usually like understanding what's going on helps even to solve like an engineering problem, right? It's kind of important. And like some people say like, maybe, but we don't have time for that. We just like, mix measure, because like the pressure from the community is so high that basically if we don't do that, we kind of lose whatever, we don't, I don't know, publish as many papers, I don't know.
Oh, wow. Okay.
So what we try to do is to develop some simple models that could describe such materials. And so basically there is this chemical problem of this, like, materials, like mostly studied by chemists, material scientists, and we wanted to do some kind of quantum physics perspective on these materials. And in physics, there are a lot of models which are also interesting per se. So these models they're not supposed to describe real material, but the logic is, like, it's very, very much how physicists think. You have some very complex system, some very complex material, or some, in biology also, some very complex system. What is the simplest possible model that would describe the behavior or like some key features of the behavior of the system? What is like the simplest possible model? Because if we find it, we already learn a lot about this complex system, even though, of course, the simplest model is not like exactly like describing it. But, if you can reproduce it already in some very like toy model, it means that, we have insight into the behavior.
Yeah.
And for example, in physics, there is a so-called Hubbard model. So this model represents a crystal is like some sides, some discrete sides, and electrons hopping on the sides. And then many electrons interact with each other. And of course, this model doesn't describe exactly like any particular material. But for example, the question is like, do we see some phenomena like high temperature superconductivity in this model or not? And like if we do, then we already learned a lot about like high temperature superconductivity, for example. And the same we wanted to do about this perovskite. So we designed a simple model where you have some sides on which electrons hop, and then in between the sides there are molecules that rotate, and electrons interact with these molecules. And you could already show that in this simple model, you explain why these materials are good for solar cells, for example, why electrons live a long time and do not recombinate with holes for a long time. Already, like you see it in like very simple toy model. And that brings us a lot of understanding. And then we can also predict some effects that are very hard to see in like quantum chemistry computations. If you have like a real computation, density functional theory, molecular dynamics, it's all very useful. But if you do it, it's very hard to see like sometimes what's going on. And in the simple model, we can predict something and tell experimentalists, okay, go look for it. Maybe you won't find it exactly looking like that, but it will be something very, similar.
Mm. And how often do you refine your actual model? So when you have one, how often do you have to iterate that it actually represents later on that what you see, or is it just you make the model and then you measure again? How can we?
Well, so there are two aspects. The models are interesting per se. So it's also like if you have a model to see, because solving the model is very complicated, right? And solving the model also requires new theoretical tools because we're talking about quantum and many body systems. So it's many interacting particles, quantum, and it is impossible. So basically, exactly, you cannot solve more than, I don't know, 10 interacting particles of the quantum level, like exactly numerically, not even not like equations, but
Mhm.
like so because quantum problems like scale very badly, and you need approximations, and it's also interesting per se to solve this problem and see like a model and see what new phases emerge,
Mhm.
and then you can change the model, you can compare it to experiments, so it can also be parallel business. So theoretically it's also very interesting, and it counts as a result in theoretical physics
Mhm.
where you like study the properties of the model because it shows like what is possible, it's like
Mm.
how do you describe, like you develop a language to talk
Mm.
about that.
Mm. Mm. And how many models do you have now established to be true?
Okay, but what is true? I mean, models are like, you
Or
know,
represent what have been measured, let's
I
say.
think it was George Box, like it was a statistician who said all models are wrong, but some of them are useful, right? Like true is absolutely not how one can describe it, because like what is true or false, models are is something that helps us understand like approximate the nature,
Mhm.
and try to express nature in some kind of language of math, right? And like so, which models are helpful. I mean, like every model we develop, actually, like all models one develops are helpful actually,
Mhm.
because
Mhm.
even if it doesn't work, the things like if it disagrees with experiment, you also learn a lot. It means that okay, this doesn't describe the reality, and it
Mhm.
means that, well, we learn a lot because it means
Yeah.
that the reality is not like these things that you thought were relevant are actually not relevant, and
Mhm.
then you have to look more, but like you understood a lot, and
Okay.
basically every single thing you do as a theoretical physicist, if you're like sane or whatever, if you're like uh, doing it consciously, it is useful,
Mm.
because like you learn something either about the model, like what is possible theoretically, which gives you ideas about like future experiments, or like if it agrees or disagrees, it's still extremely useful.
Mm. Okay. No, I just wanted to know from you your future goals. So, what do you envision maybe in the next 10 years to be doing to be maybe, I don't know, if like maybe you get the physics Nobel Prize.
Well, what I'll realistically be doing, well, it's a good point um, about being a scientist, that you actually don't know what you're going to be doing like later, like when you start working on some problem, you don't know how you finish your day sometimes, and maybe like, or you go to some talk and get some ideas. So actually I don't know, it's kind of a random walk
Mm.
uh, in some sense. I mean, I would like to do something very different, actually, using physics and maybe some, linguistics or some sociology or some like, biological applications as well. So we try to do a little bit of something barely related to biology. I can talk about it a little bit, but I'm definitely very ignorant in biology, unfortunately, as well. Many physicists are. Uh,
So I was telling that we have this collaboration on the podcast. So biology meets physics. So that's
exactly.
yeah, that's why I find it very interesting. Okay, but I think it's also a bit of problematic because you're in academia. So of course, securing your position to be a permanent position is also something that is really important, and also getting funding to actually continue your research. So I think that's also sometimes a bit difficult to get uh, together, right?
Well, I have a permanent position since like 2019, so I'm not worried about that. And also the funding situation at my institute is very good.
Mhm.
And I'm not worried about that either. I'm worried about not having good ideas and not meeting right people. I think it's more important. I think people complain a lot about funding. I mean, it's true, whatever. Like you can, I think like if you have good ideas,
Mm.
there is always a way to find funding. I mean, permanent positions is another thing. Like if you have like 2-year contracts as a postdoc,
Yeah.
of course you cannot just like spend like 2 years not publishing and thinking. I could do that in principle. Like I could just start like switch to biology and start doing it and learn like for 2 years. But anyway, of course, like permanent positions is a huge problem in science.
Mhm.
I had the video also like that academia looks like a drug gang,
Yeah.
basically like a Drogen cartel. I mean,
Yes.
it's not my idea. It was an article about it,
Mhm.
but it's kind of true. Yeah.
Mm. And how different would you say is the situation for physicists? And I don't know if you compare it to colleagues in chemistry and physics, in biology. How different is the situation there? Is it hard to get to a professorship?
I mean, we have like actually quite an interdisciplinary institute, so we do not have departments, and we talk all the time with like biologists, chemists. I mean, I think biology from or like life sciences, from what I've seen, uh, it is extremely competitive, and so I see also people who work, for example, like 5 years on one paper, so they publish like paper in Science, Natures, or like top level, but just like one, and this is like a huge pressure, right? Like you either publish it or not,
Yeah.
because in physics you publish like usually more. I mean, depends on the field, but usually like you have several like very good ones or like a bit more like just good ones. It's like easier to evaluate just one paper. I think in biology there is a lot of pressure. I mean, like in life sciences, like I see like people working with animals,
Mhm.
and I hear that postdocs are longer.
Could be,
In the
yeah.
chemistry, I think it is actually probably easier because, well, depends. But like a lot of synthetic chemists, they do very fast postdocs because they publish very fast. It
Mhm.
depends on the field. But like
Mhm.
some people do like just 1-2 year postdocs even because they are just publishing a lot of papers
Mhm.
in synthesis, for example. And in my superficial impression,
Mhm.
and there are a lot of jobs also in the industry, in like all over the place. I think more than in biology.
Oh, okay. So physicists go to the industry and work there then.
Well, I mean the chemists. I mean, I think physics. I mean, a chemist. I mean, in physics is different. Like there are I think many more jobs. Like from my like naive perspective, many more jobs in chemistry just for chemists, where
Mhm.
you can really work on what you've been doing.
Mhm.
Than in physics or biology. In biology, I mean, there is pharma. In physics, there is industry like whatever semiconductors. Now with quantum computers, there are a lot of startups. But in physics, it's different because in physics, you learn a lot of skills that I have people like from my group that work at Google doing machine learning, right? It's like not physics, but a lot of physics do programming. They go to finance and whatever. And not many biologists are that good at programming, for example, right? I mean,
No.
there are people doing bioinformatics and so on.
Yeah.
But so what I mean, like in physics, like there are almost no unemployed physicists, but it's also because if you do like theoretical physics, like largely you can do anything basically. I mean, of course, like no one is going to hire you to do like biological like stuff in fire. Like you don't have expertise for doing that, but
Mhm.
basically things that you can learn, like programming, like machine learning, even if you haven't done that, like
Mhm.
consulting, whatever. Like a lot of people just jump and succeed there.
That's very interesting. I didn't know that. Um, Maybe before we come to the part where we talk about your beautiful YouTube channel, I would like to know from you what is the most beautiful moment or moment in recent years you had in your research.
My research. Well, I mean, it's hard. I mean, it's hard to single it out because it's like you should maybe ask people in my group because it's like there are several projects and we had several great results in these projects. And I think if you ask PhD students or postdocs, maybe I hope they will call it like a beautiful moment in their research. But I mean,
You know
it was
now.
also because for me, like okay, there were like several years ago when we had like this like Angulon quasiparticles and like we were comparing with experiment. It was like nice, but I mean, after a while, it's also like okay, like. It's like your job and like I'm trying to make it beautiful
Mhm.
for people working in my group rather than like you know uh, taking it for on my own account, you know.
And maybe as a last question is, how do you balance your personal life with your research or working life? How easy or difficult is it for you?
Well, it is very difficult. So I have I have a wife and a daughter, and my wife is actually doing pursuing a very ambitious career now, as well. And like I mean, I have a permanent position, so like I can, so I'm basically like
Mhm.
I spend a lot of time with my daughter, which I enjoy very much. But it's also like unfortunately, modern society, I'm sure in Germany as well, in Austria, like it's not suitable for well, even though we have like of course Vienna is like super good in like nice socialist things like kindergarten and like all the things, but nevertheless like when two people work full time and you do not have like family like grandparents that could help you because we're both foreigners, it is like I think the society here is not really suited for that,
Mhm.
but well, at the moment my group is working very well, and the input that I need to provide is kind of relatively small. So as I described before, it was like it's a lot of this. There is this joke about a guy coming to fix his car,
Mhm.
and like a mechanic like takes hammer, hits, and
Yeah.
the problem is fixed, and he sends a bill. It's going to be like $100 or whatever, and the person is like outraged. Okay, what does it mean $100? Like it's just one hit of the hammer. Okay, I'm going to provide a
Mhm.
detailed like Rechnung, like detailed receipt that hitting with the hammer $1, knowing where to hit is $99, right? And it's kind of similar. I feel a bit like that mechanic because uh, it's like sometimes I like enter the group meeting and like one remark that I provide, like people are stuck and they would be like, okay, like try to talk to this person or like whatever. Like, have you thought about that? And it's like 2 seconds and it solves the problem. And okay, it's like 2 seconds work, or say 2 seconds work per day
Mhm.
was super helpful already, right? Because the project got unstuck and people are working and like it's going to make progress.
Mhm.
But it's not 2 seconds. It's like 20 years of my experience that allows me to solve this problem in 2 seconds, for example, or just to randomly say something that I don't even know is going to solve the problem, right? I'm just like brainstorming. Okay, it's actually was useful and like kind of all these like leadership things, like providing the atmosphere in the group and like talking to people. Sometimes it takes actually very little time, but it's actually all this like 20 years of my experience
Mhm.
that allow me to spend sometimes very little time
Mm.
and make the group run and successful, and
Mm.
we are publishing well and so on. And I can also like spend a lot of time with my daughter and like sometimes like I have some ideas like say like in the shower or like
Mm.
spending time with my daughter that can be also useful. But it's not you don't need to physically sit all this time like 40 hours at your desk, right? It's like in some jobs,
Yeah. Yeah.
right? So I can find this balance, but it's like also I'm in a uh, very privileged position as a tenured professor,
Mhm.
and also I mean we are extremely privileged to be doing what we're doing. So I have to admit.
Mm. Thank you very much that you were openly speaking about this. As I said, you have this beautiful YouTube channel in German. And I translated your motto that you always say, you've never experienced physics like this before. So I would like to know from you, why did you and how did you start with science communication? What drives you to explain specifically complex physical science topics?
So it's a difficult question. So I always had this kind of drive or like need to tell stories. As you maybe on this in this interview, I'm also talking too much. But you see, I'm like, I have like no one listens to me at home, so I have to talk in front of the camera for my like 28,000 subscribers or whatever. But I have to like I always wanted to write something. I had a blog in English as a PhD student, and then like now sometimes I write for newspapers also in German or like some whatever. Like I like speaking in front of the camera, and I don't see actually myself too much as a science communicator. It's more like a professor with a YouTube channel,
Okay.
and the stories I tell, it's also like, yeah, I mean they're quite random and a lot, very often improvised. And for me, honestly, it's like a form of art. So I'm not joking, because like I have like I'm doing everything myself. So I'm like filming, and like I do like sometimes like in the early videos that I recorded during Corona, I probably was showing more of that, because I also back then didn't have a daughter and like had a bit more time, like some like tricks with camera, like things that I do in the cut, and so on, like the way like I tell the story. So for me, it's like form of like self-expression. So it's like basically like need for self-expression realized through that. So need for self-expression comes first, and then okay, how can I self-express myself? Like the thing I know is like physics, so I can talk about physics. You know what I mean? So it's not like I need to talk about physics and how I do it, but it's like I need to be talking, I need to be like doing like making videos, doing something creative, and like okay, like what would be the topic of that? Like okay, I couldn't be talking about cars because I don't know much about it or whatever. I could be talking about physics science because I have expertise, right? But like the drive is actually expressing my creativity. I don't know why in German. Partially in English would be much easier, and probably I would get more viewers. But I actually wanted to learn German, so that was one of the reasons. Because in institute we have an international institute, and it's actually this institute is very different from an average like German Austrian institute. We have like basically we don't do anything in German here. It's all like English on campus, and there is no opportunity to like learn German even. So I wanted to have some activity that lets me regularly speak German. So I basically speak German only on YouTube, on interviews, sometimes on podcasts, in the articles I write for newspapers sometimes. But basically, I don't speak German at work or at home or in supermarket, whatever, like with some friends. But I mean,
Oh, that's so I just recently discovered you, so I do have to say I would have not expected you to be doing this to learn German, because your German is so good. I always understand everything. So it's really cool to know that you're kind of like practicing with your videos. But I think yesterday you uploaded another video, and I was really fascinated about the fact that they started to build again this mega collider thing again.
well, I don't think it has been decided yet, but it's like a very serious proposal, and I don't know. I'm not following exactly. Like I
Mhm, mhm.
expressed my take on it, but
I was shocked that it would take 40 years to even build this thing. And then you said it's 13 milliarden, so it's
yeah, 30 billion. Yeah,
$1 billion or euros to spend in. And I really liked your last part of the video where you said it would have been better to actually take part of this money to make actual benchtop science first and see which of the theories apply before you have these kind of
yeah,
big, yeah.
and this already exists, and this is, I mean, this is not like just already exists, but for example, like the best tests of like possible supersymmetric theories, they come from these very cheap experiments
Mm,
on like tabletop, like
mm,
experiments with lasers and molecules, and not from the Large Hadron Collider
mm,
that had an ambition to do that, right? So
mm.
actually, the tabletop experiments, in some, it cannot replace. It's not the same,
No.
but it also can provide a lot of insight, and almost the best insight we have
Mhm,
in some of the field is actually coming from cheap
mm,
experiments.
mm. And because I'm not so into the physics, but why do we need such big instruments? Can you elaborate very quickly on this?
Yeah, so we need such big instruments to achieve higher energies. So what these instruments do, they spin and they accelerate particles very fast to very high energies, and they collide them, and then they see what like at such energies the particle disintegrate. I mean, it's like like it's all about energy, not mass, and it's not like particles consist of stuff like literally, but you create a lot of particles and then you detect them. And that's why LHC was built, like Large Hadron Collider back then, that there were like a lot of things that they promised or they promised to test or like wanted to test and tested. But the main thing was to find Higgs boson that was predicted to be born at high energies that they achieved. They achieved these energies and like they literally detect, they really detected the birth of this particle, and so it was detected. But then, like they didn't measure much of other predictions that they had about like physics beyond the standard model of particle physics. And because there is a standard model that explains a lot, now Higgs boson kind of closed the gap there, but it doesn't explain a lot of other things that we know is true, right? That we know experimentally. Standard model doesn't predict it, doesn't explain it, and the new collider probably can provide insight into that, but it's like a lot of investment and a lot of like kind of pulling money and effort away from other fields that might maybe also could provide some insight into that.
Who actually decides on such big projects? Is it like a European Commission or?
I actually don't. I mean, I could find it out, but I don't know exactly. There is some committee. It's very serious. There are scientists. There are European bureaucrats. I'm sure there are like each country commits and sends like And the question is like Germany was like discussing, do they sign or not? Maybe they will not sign. Like they will not provide a contribution if it if it doesn't if it gets too expensive. Or I mean, it's a very complex bureaucratic process. I'm not super interested learning much about it because whatever. I mean,
Or
there is. I mean,
you become the head and spend the money more wisely.
yeah, I better comment about physics and these things. I mean, European bureaucracy is a thing of its own.
Yeah,
I
that's
have
true.
I can comment about other things, but
When we come back to your YouTube channel, I would like to know when you present your your project, sometimes also in the videos, but also talking about physics topics. First of all, how long do you need to prepare the script, for instance? How long do you need to edit? And what topics usually you take? Is it something that you go by the algorithm, or you say, no, that's something that is interesting for me, that's why I do the video?
yeah, I don't write any script, so I only I put bullet points not to forget stuff, to mention things. So I used to write, but it's mostly because of like German, like because it was very challenging for me when I started like 5 years ago to do this in German. Also, my level of German was not that great back then to improvise, and back then I would write like scripts for like the first 5 videos maybe, and then like for the rest 146, I don't know. There was no script because I do not believe. I don't believe in scripts for spoken. I know a lot of people do that, and a lot of like I took part in some like comedy improvisations, whatever. Like and, like some people like writing and rehearsing. I mean, it's not like I believe in preparation, so I think it's like one could prepare. So it's not that I think one should like not prepare. Definitely, I'm not saying that, but the problem with scripts is that written language and spoken language are two different languages, and it's the same with talks, right?
Yeah.
Like as soon as you write it, you subconsciously polish it to the written standard, kind of, and you do not speak the way you write. I mean, some people do, and this is very very boring, and like usually the way you speak is just different. Like well spoken and well written are two different things.
Yeah.
And for example, when I prepare talks, I'm not doing that with YouTube videos, but okay, I don't do that anymore because I gave so many talks. But for example, you have like ERC interview, like some super important talk, or I don't
Yes.
know, some like thesis defense, like super important talk. So I would not write it, but I would rehearse it many times, and unless it sounds well as a spoken word to my standards, right? Instead of like writing it and then trying to many people write down their talks, and I mean whatever works for them, but I mean for me it's not optimal.
Mhm.
And for YouTube videos, I kind of do the same, so I don't rehearse the video, but I basically repeat like paragraphs in front of the camera spontaneously unless they sound good, right? And then I
Yeah,
cut, right?
yeah, yeah.
And then I have like same like 4 hours recording that then results in like 20-minute video,
Mm.
or what are maybe two
Mhm.
hours 3 hours recording, depends. uh but I basically like just speak freely, and then what sounds good when I like until I polish it like in the spoken fashion, and then I'm happy with that instead of like writing it and then trying to pronounce exactly. Uh, that works for me better. I'm like not judging what other people are doing. Uh, so approximately, it usually takes, I don't know, 2, 3, sometimes 4 hours to record. Same amount, approximately like 3, 4 hours to cut.
Mhm.
Uh, yeah, and preparation. I usually like think about like what I would like to talk. I mean, it's not about the algorithm. The thing is like I would love doing something for the algorithm, but I have no idea. I have no idea what's going to be successful or not. I'm sometimes surprised by the videos that are going successful,
Mhm.
and surprised sometimes. I think my videos are going to like some videos like more provocative, and like it's not going anywhere. Doesn't get many views, so I have
Mm.
no idea why.
Mhm. Maybe it's just the topic because I had two videos about or two podcasts with two medical professionals who are either from preventive medicine or someone who is working on chronic hepatitis B. And I would say these are two important topics, but they didn't perform so well. Last time I had now someone who is working on CRISPR, and suddenly the views got up.
Okay, but CRISPR is like hot topic, right?
Yes. So it was unintentionally. I didn't expect that. So I don't know. In your case, I don't know the quantum mechanics of microplastics or something like this.
Yeah, I don't know. I mean, what goes well is like, I mean, I had this video about Sabine Hossenfeld. I mean, it's like, it's not like viral, but it's like, but okay, this I expected, and I didn't do it on purpose, like to leech on someone who has more views because like okay, like many more people like know Sabine and like
Yeah.
they get attracted. So I expected that, but there were some people, some videos that I had about chiral molecules actually because uh, I was talking about some like some scandals where you have like medicament that has two enantiomers, like one can kill and another one works as a drug and so on. Uh, yeah, this type of, but I mean, or some like chemtrails, some like 5G,
Yeah.
some like conspiracy theories. Like yeah, these
Mhm.
videos work well, but I
Okay.
mean, sometimes I'm doing it, but like I'm not following. It's not like I don't have a good feeling. Like I have no idea who is my focus group actually,
Mhm.
our
Mhm.
target group. I don't know who is watching my videos.
Mm. So one biologist.
Yeah, it's good. Thank you. Like it's very nice.
So maybe also you are more on YouTube. You're not so present on like Instagram, I guess. I saw at least you're not uploading as much as on YouTube. So I wanted to know from you what kind of changes do you see in different social media platforms when you compare to YouTube? How your content is provided?
So what changes? I mean, I'm present on Instagram, but I treat Instagram very privately. So I think it's open account, but I'm posting just stuff like with my daughter or
Oh, okay.
some like memes, some stupid jokes and so on.
Hmm.
And I'm not excited about like posting on Instagram. I don't know. Like I used to post short form content on YouTube at some point.
Hmm.
So I used to post YouTube Shorts, and that almost killed my channel. And
Oh.
then I started. I used to. So then I actually found some videos on YouTube that explain why it happened to a lot of people. And if you look And big creators, everyone had this phase. They started posting shorts and then stopped. Like most people don't post shorts because then you basically get a lot of people. So even like shorts get promoted, and then for some reason people watch shorts, and then the shorts do not act as an ad for your long-term videos. No
Yes.
one
Yeah.
follows
I saw
to your
that.
long-term. So basically, people start watching shorts and they just give up on your long-term content, and that's not good. And they just stopped posting. Like I erased my shorts. I made them private, and they recorded a video about it that it almost killed my channel. Although I find short form content kind of good sometimes, but it's kind of not the content that I think is good for like your brain chemistry, that you get addicted to
Yeah.
this like swiping, like short dopamine peaks
Yeah.
and so on. And at the same with like Instagram Reels, TikToks, whatever. Like
Mm-hmm.
I don't know. I think it is interesting. Like short form was like booming, but now I think it's not that much anymore, and like part of it is very hard to monetize it for the platform. So like TikTok is really bad with monetization, and like also for creators, but also for the I mean this is not why I'm doing it, but platforms like YouTube wants to show ads, right? And short form is very hard to monetize, and that's why they are not actually pushing it as much as they used to, my feeling. And YouTube is actually putting a lot of effort on to promote long-term content, because they want to compete with like Netflix,
Yes.
like Disney Plus, and just TV. And I have a feeling that when I record like 30-minute videos, sometimes I'm not doing it on purpose, but sometimes like whatever, 30 minutes, 20 minutes, my videos got longer somehow in the last year, I think. Uh, Not consciously, not on purpose, but I think YouTube likes it actually a little bit more.
Yeah.
I think YouTube more because they can put like more and more ads in it, or like is like replaces Netflix. I don't know.
Yeah. I just some days ago I saw actually changes in the YouTube Shorts algorithm. So now it actually promotes or should promote your long form video. So if you have a snippet out of your podcast, for instance, it actually helps you to get more views on the longer form because people get there. That was not the case before. So I saw this kind of shift a bit more. So that's why I started also again to post a bit more shorts so people actually get into it and think about uh, what we are
You
talking.
mean this clips function? No, or
So so you make shorts really, and just you can make a link that people get directly to your long form video.
yeah, but that was the case before as well. But
So
no one would click the link.
they changed now the algorithm that
Okay,
you actually push the people to watch the long form then.
I see. Nice. Okay, I should check it out. Yeah,
So maybe you give it another try. You know,
sure. Yeah, I like. I think yeah, like a short
again, your
form
channel
is good.
stop it.
Yeah, like short form is also good as some kind of like there are sometimes like some joke or some interesting like quote I have like in the end of like 30-minute video, and no one is like watching that long, and it's good to put it somewhere.
Mm. Maybe as a last question, then we hop over to the next section. Um, how much do you prepare in advance, or do you make a video when you feel it?
Well, I always like I finish the video and I already start thinking like in the background what could I record next.
Okay.
And it depends, right? I mean, sometimes I have good ideas. Sometimes, like I used to panic a lot, like in the beginning, like okay, I need to produce whatever.
Mhm.
Now I feel like okay, this is my hobby. I don't need to produce.
Yeah.
But basically, what happens that I have good ideas and manage to record videos pretty much every week because I like the process.
Mhm.
But it's like a lot of psychological thing. If you push yourself too hard, okay, like I have to put it out like every week,
Yeah.
like it makes you miserable at some point. And also sometimes like okay, like why do I get like that little views on some videos? And now like I try not to care, but enjoy the process, and somehow like because I'm kind of relaxed, I manage to in the end I produce like approximately one video per week, and
Yeah.
yeah, but it's very very random. Like I just have random ideas, and then okay, like it's interesting, some
Mhm.
crazy idea or
Cool.
some interview, whatever.
It's the same for me. I was stressing out in the beginning as well because whenever you listen to some of the YouTube video people, they say, "Oh, you have to publish, I don't know, once a week and to grow your channel." But in the end, it's for me also not sustainable because I have to be in the lab and do my work. I'm not a 100% content creator all the time. So I completely get it. And I really find your videos very engaging and open, and and you get the feeling that you really care about the topic that you're talking, and that's something. So the honesty behind it, and also that you're open and say, well, that's my opinion, is something that I really value. So I want to thank you for that.
Thanks.
Good. So we come to section 2, because I would like to talk to you what's the difference between a physicist and a biologist. So you said you would like to go a bit more how quantum dynamics or the stuff that you're doing could also be relevant for biology. Um, so what I would like, or as a beginning of this section, I wrote down something. So, biological systems are filled with molecules that rotate, interact, and transfer energy in ways we are only beginning to understand. But how these movements shape their function. And in your research, of course, you do quantum physics in the concept of Angulons. I hope I said it correctly. So, by understanding how molecules behave in complex environments, you could bridge the gap between quantum mechanics and molecular machineries of life, if you want to expand, right? So, first of all, what are Angulons? If you could explain that to us.
Yeah, okay, but Angulons is one of the models. I can explain it, but like it's not really that relevant to biology. Maybe there are some applications, I don't know. But then we can talk. I can tell you about another project that is actually
Yeah.
probably relevant to biology a little bit. Well, Angulons is a kind of new quasiparticle we suggested. So some people say discovered quasiparticle. I mean, you can say that, but quasiparticle is a model. So what is a quasiparticle? So you have like particles, right? Like it can be anything, like also electrons or whatever. And what quasiparticle is like when you can consider many interacting particles as one particle with some properties. And an example that I always make, and I mean, it's like physicists like this example, is a running horse. So imagine like you look out of your window and you see like a horse running in the field, right? And then this horse is surrounded by the cloud of dust such that you can barely see that horse, right? And you like your brain already like thinks in terms of quasiparticles, even if you have no idea what that means, because like no way you would say, look, I have no idea what's going on. Like I see like 1,000,001 particle, like million dust particles, one horse, and like I have no idea. It's like all too complicated. You will say, like, I see a horse which has a little bit different properties. Like this horse is like dirty, is like it probably cannot see that well because it's like surrounded by dust. It's like slower, whatever. So like it is like quasi horse, like it's like horse but with a bit different properties, like surrounded by cloud of dust. And the same in quantum physics. So for example, if you have an electron moving in a crystal, right? So electron moving in the crystal interacts with like millions, billions of trillions particles, with atoms, with other electrons. There are like vibrations of crystal lattice, whatever. And this system is extremely complicated to describe. So to describe it exactly, it's impossible. There are some models, but what is possible to do very often is to note that an electron moving in the crystal moves almost like a free electron, but with a little bit different properties. So the electron actually gets dressed by interactions with other particles in the crystal. So it kind of collides with other electrons, with other photons, with other whatever, like with other like atoms there in the lattice, and it gets dressed by excitations of the crystal and behaves like this quasi horse. So it's like electron dressed into a coat of excitations, and it behaves like a particle which is almost like an electron, but it has a larger mass because it has like feels this drag of interactions from the lattice. And so this is called polaron and quasiparticle. And so you can describe electrons using this like concept very accurately. And we did kind of the same for molecules, but for rotating molecules. So molecules rotate in some liquid, like it was like quantum system, superfluid helium, and we described it as some quasiparticle we called Angulon, that is like a rotating molecule dressed by a cloud of excitations that are also kind of rotating. And then we showed that these quasiparticles exist in experiments, and they can be used to describe and to simplify the description of experimental data. And I mean, we don't have any applications to biology now. I can tell you about other projects that might have. But in 2 words, that's what we like. What Angulons are.
Yeah, then we just directly jump into it with biological background or applications. So what would you or what kind of projects do you have where you have a bit more biology integrated?
So we work a lot with chiral molecules, and as biologists, you know that everything that we have is chiral, right? Life is chiral, and for example, like most amino acids that we have are like kind of left
Yes.
chiral. Most sugars are right chiral, and we do not really understand why. Like, why is life chiral, and what broke this symmetry at some point? Because, like, from the physics perspective, these things should have the same property, right?
Yeah.
And of course, you know way more about that for sure. That like all drugs or like all like medicines are chiral. So like if you have a ibuprofen,
Yes.
it is actually like it's a racemic mixture. Is like both chiralities are present in the ibuprofen, but one of them, I don't remember which one, doesn't do anything. It is safe, and the other one is actually like works as a drug. And there was like in Germany this famous Kontergan scandal. I think it's like so it was thalidomide is the Wirkstoff, right? Is the that it was medicine against morning sickness in pregnant women, right? And like so, what happened that babies were born heavily handicapped, right? Like. Without arms, without legs, it was really horrible, and it turned out that there are like two, like enantiomers, two chiralities there, and one of them works as like a very effective drug against morning sickness, and another one is basically like killing the fetus or like making horrible like changes to it, and they were using a mixture of that, like racemic mixture, without purifying it, and so. Understanding chirality, why life is chiral, why the world around us is chiral, is a huge challenge, and also separating the drugs, for example, separating the molecules into like left and right chiral is also very, very important. And there are a lot of like physics theories, like why life is chiral. For example, I don't know the status exactly, but there was an observation that cosmic background radiation has some polarization, so it's not completely like unpolarized. It has some polarization, and maybe that broke the symmetry in like left and right. It's very hard to prove, of course, because you cannot have like origin of like you cannot have like formation of life on Earth again to check it like quick, like whether microwave background radiation or some other things like that made the symmetry breaking possible. But there are interesting physics questions, and there are like questions, from the physics perspective, left and right are also like they are not equal. There is weak force in nuclei that breaks the symmetry. It's extremely weak, and technically there are like left and right chiral molecules. So if you take like left protein and right protein like of the same sort, there must be a little bit like a super tiny energy gap between those two, which should be possible to detect with like super precision spectroscopy. And I knew a person, like there are people who spent their entire careers in chemistry trying to find this like separation. Like they failed so far, and like there are people who retired without having found it, but it should be there. Like just very hard to detect. Whether that broke the symmetry, we don't know. But anyway, what I'm doing also as a physicist is so-called chirality-induced spin selectivity effect. So what is it? Like CISS, so chirality-induced spin selectivity. It's kind of fascinating. So chirality, like in molecules or like in materials, is one aspect. Then there are two more related aspects. So there's chirality, there is light, so such a triad. So chirality, light, and magnetism.
Mm-hmm.
All of these things have something to do with each other.
Mm-hmm.
For example, chirality and light.
Mm-hmm.
You know this, middle school experiment where you take a solution of sugar,
Yeah.
you take like laser pointer, like linearly polarized, and you observe polarization rotation, right? Because light interacts differently with like left chiral molecules, right polar molecules. So this is quite well understood, and this is like basically high school or middle school experiment with like polarization rotation.
Mm-hmm.
This was like, I don't know, 18th century. Like, I mean, this is like very old things. Then chirality is also related. No, magnetism is also related to light. So there's like chirality light, then light magnetism are related with each other. So it was also like there were all these effects. What is it, like Faraday Carey effect, whatever, like where you have magnetic material, because magnetism like breaks this kind of time reversal symmetry, whatever. Magnetism is also kind of similar to chirality and to like light polarization. So it was known also for like century or 2 centuries that magnetic materials can rotate polarization of light. So magnetism, light was also well established that you can couple those. But the fact that you can couple chirality to magnetism directly, it is very new. It is kind of 20 years old. Like there were papers starting from like 99, where people observed that if you take a chiral molecule, you drive current through it, and electrons have a spin. Electrons have like spin up, spin down, and spin is like corresponds to a magnetic moment. So it's like the little magnets.
Yeah.
And you drive current through this chiral molecule, and this current becomes spin polarized. So you just drive normal current, and you observe that only like spin up comes through if you have like like right-handed molecule. If you take left-handed molecule, then like spin down comes through, for example.
Okay.
And if you tell it to a theoretical physicist, people would be like, okay, it makes sense, because you have kind of, imagine a DNA. This is like a magnetic coil, right? Like if you drive current through DNA, you have a magnetic coil, so it should have some magnetic field, it should couple to spin, and then, okay, it makes sense that, you have some effect. Great, you calculate it, you get an effect like 10 to the minus 4, 10 to the minus 6. So thousands, 10,000 of a percent or whatever, like very small effect. Why? Because, well, I don't know, like it's relevant to your audience, but organic molecules consist of very light elements. They don't have strong spin orbit coupling. So for light molecules, because they also, like organic molecules is what is like hydrogen, oxygen, nitrogen, carbon. These elements do not have strong interactions with spin usually, naturally. So you have effect, but this effect is super small. And in experiment, it is super robust. So this situation is the opposite of like what theoretical physicists usually do. So in theoretical physics, we like, we predict some fancy effect and say, okay, just go ahead, measure it, and stuff is complicated. And like an experiment, you need like pure material, you need like very precise measurement is very hard, like low temperatures, like it's very difficult. Here is the opposite. Theory predicts very small effect. In experiment, this effect is like 60%. 80% at room temperature. Like just put molecules on substrate. There are different ways to measure it. Like effect is like on the order of 1. It's like super strong effect. The current is like 80% polarized, 60% polarized. Any temperature, any substrate, different molecules, like chiral molecules. And we still don't understand what's going on. And there are a lot of papers trying to explain this effect, like including ours, trying to understand the different contributions of different kind of components. It's very hard. It is also very important because, for example, it can be used to couple directly. Well, this effect couples directly magnetism to chirality, which, for example, allows to separate enantiomers. So, for example, there are papers from our collaborators where they, if you polarize current going through a molecule, it also means that different chiral molecules will have different magnetic properties. So, for example, like magnetizing, like you can magnetize like like right-handed molecule in this direction and like a left-handed molecule in this direction. And for example, it was shown that if you take a magnetic surface, you can separate enantiomers. So you will have only like right-handed molecules attaching to it if it's like magnetized up. And you flip the magnetic field, and like only left-handed molecules get attached to it. And there was a science paper from a few years ago, and they were like, so it's real in the lab. And again, like it's funny because the theory is like it kind of makes sense, but the effect should be so weak. We don't understand why is it so strong, why experiments are so robust.
Yeah.
And this is relevant to biology, right? Because you can separate enantiomers, and maybe we'll understand some like the way, like better the way the chiral molecules are produced in biological processes, right? From non-chiral ones, from like quantum perspective.
I think Martin Moda made a good video about it, about what's called mirror lives, right? And how dangerous they are. That's why this whole field of mirror lives was or should be shut down or not explored anymore, because exactly the whole body and in general life is made a selection towards specific forms of the molecules. And if you would do the opposite, it would actually not work anymore or even cause harm. So like he was presenting like antibiotics, for instance, they would not work anymore if they would be in a different, if they would be in
Different
from,
enantiomer, yeah.
yes, yeah.
Yeah, I mean, I'm excited about mirror life, and like imagine we could like create opposite antibiotics, but the life is also opposite, right? Like all like amino acids are like right-handed, sugars left-handed, and like would be super nice. Like, yeah, I like that biologists came from counting frogs to creating mirror life. I think it's amazing. Like finally,
Yes.
that's kind of biology, like okay, not the biology we need, but the biology we deserve, whatever.
Mhm.
But I mean,
But it's really interesting what you're working on. And what are the like future projects that you have that would include a bit of biology?
well, I mean, I'm super excited about doing something. Like honestly, like I don't know. Like, so we're going to work on this like magnetism chirality, and then like I wanted like I mean I'm trying to understand some very basic things. Maybe someone could help me because like trying to understand some very basic things of biochemistry or whatever. Because like if you think for example, how chiral molecules are created in our body, you see that they are created by some centers, right? And you have like these molecules, like there are molecules that create like chiral molecules from non-chiral ones,
Mm-hmm.
and all of them contain magnetic atoms.
Mm-hmm.
Like they contain like magnesium, manganese, or whatever. Like, and this is like a center, and the question is like does it have anything to do? Is this also something that couples magnetism to chirality,
Yeah.
for example, or is it just random? Is it just that magnetic atoms also have like open shells, whatever, and they allow for the molecules with different geometric shape, and
Mm.
this like geometry just mechanically makes chirality, and like this is like question like I think
For
people,
if
yeah,
you're interested, so if you take, for instance, DNA binding proteins that have these so-called zinc fingers, right? So
for
already
example, yeah.
the name tells you zinc is mainly important for the building of the zinc fingers to bind properly. So there has been experiments done where you take magnesium, for instance, and then you introduce instead of zinc magnesium that completely destroys the zinc fingers. So, and that one is even not reversible anymore, for instance. So that would make sense to analyze what is happening there, why, for instance, this has a huge impact on the protein then itself. And there, I think it also has to do on the very, atomar level. For I think it has to do something with that. It's something that's really interesting.
Yeah, I know. I mean, it definitely has like everything is quantum because like binding like chemical bonding is quantum, right? And like whatever. Uh, Yeah, I mean, the question is like, for example, like, is it magnetic property relevant at all of
Mm.
these atoms, or is just some kind of chemistry that makes the molecule weird shape that is like
Yeah.
then is useful for the function?
Yeah. True.
But I mean,
Not just
I don't. Maybe it's known, but like yeah. I mean, I wish I knew more about it.
I don't think it's from the biological perspective, it's not known if this magnetic component would have an influence on the function of the protein. I could only imagine that since maybe magnesium is a bit more stringent than zinc, that this might have a effect, but this needs to be measured, like that would
Yeah.
be something that would be interesting to know what happens on that level. Um, when we already talk about quantum, I think you also know there's this one Avengers movie called Quantum Mania from, and
I don't know, no, actually, but
no, okay. So that was interesting because what they did is they went into the quantum realms, and then I was just wondering if the concepts that they show were true. So they were proposing that there's a second life happening at the quantum level. So
I don't know. No, I mean there is like multiverse interpretation of
yes.
quantum mechanics and so on. But I mean, I don't know. I don't like commenting on movies. I think it's like I'm not a big fan
Hmm.
of commenting on movies. Uh, I think it's not what most active like actual scientists do. I think this kind of smart ass type of comments, like Neil deGrasse Tyson. I have to say, like, I'm not a huge fan of his.
Hmm.
Not, I mean, like, I think it's good that he does what he does, whatever.
Hmm.
But sometimes I find also what he says a bit cringe, honestly.
Hmm.
Uh, and my opinion, as usual, like very honest. Subscribe, click. No, what I mean, like. Like not censored, but anyway, because like he likes these things, like going to like movie theater and like tweeting live from a
Hmm.
movie theater, like whatever, like uh I don't know what is like Avengers movie, or like
Hmm.
or some like Star Wars movie, whatever, like
Yeah, yeah.
it's like physically inaccurate, like there are no explosions in space, whatever, there is like it's not how you land in like zero gravity, whatever, like I mean,
Okay.
I don't give a damn about it, and I don't think like most active, this like cherry picking is like, what do we say, like if you see like rom-com comedies, are you complaining that whatever they don't show like love the way it is in life, or like that whatever, that it's not like real life is not like art, it's like an art form, and like for me it's like it doesn't matter if they show explosions in space, because it's like I don't like commenting on that. And um yeah, I have like zero feelings. I mean, okay, it doesn't sound like that because I probably sound very mad. But what I mean, like, I don't have a feeling that okay, it's good that they promote, some people hear of quantum and then they whatever they want to do quantum physics. Like, I
Mhm.
also don't care. I don't think we should promote
Mhm.
quantum physics, because like it's not, like we shouldn't do propaganda. People should do it if like they want to do it.
Yes.
But on the other hand, I don't find it bad that like if they say something which just doesn't make sense.
Mhm.
It's just a movie, like movies don't have to be like, unless it's a documentary, they don't have to represent reality accurately.
Mm, mm. Um, maybe do physics-centric models oversimplify biological complexity?
I don't know. I mean, no. What is physics-centric models? I mean, physicists like simple models.
Mm,
Biologists kind of like, I mean, biology you cannot, like, sometimes maybe you can do. I mean, there are probably parts of biology where you can do simple models, but like largely it's hard to do. I mean, there are. I mean, we have here at the institute people doing nice models, like physics models,
mhm,
and publishing with biologists with very good results. And I
mm,
mean,
mhm,
but yeah, I mean, as I mentioned, physicists tend to oversimplify.
mhm,
But I mean, I think it's good when people go out of their sorry, when people go out of their comfort zone and
mhm.
try to talk, like, to speak different language. For example, with biologists, and biologists try to speak with physicists, and that's how really exciting results emerge. That they get uncomfortable and like try to understand each other and try to find the balance between too simple and too complex, right?
So we are actually coming to an end of our conversation. And usually, before we wrap up, I always give my guest the opportunity to speak to the audience and address something, in this case, maybe common misconceptions or even misinformation in the field in your working, so physics. So the audience is yours, whatever you want to say.
I don't know. I think we discussed a lot. I don't know, like I don't have a message because I'm not like
Or
I
maybe
don't have a propaganda mission. I can tell you like not all physicists are like Sheldon Cooper,
okay.
but also not all physicists are like me either. So I don't know. If you probably know yourself. I mean, what physicists are. It's not like your audience never seen an actual physicist. Maybe they've never seen an actual physicist. I don't know. Go see one.
Yeah, that's a good
Talk to a physicist today.
Yes. Go out, go to the next physics institute here and just tell people like what
Yeah.
are you doing?
Instead of going to the bar,
Yeah.
go to the physicists
Yeah.
club, whatever. Like
I think they will
go,
be completely overwhelmed because they don't know what we did now.
yeah.
Oh.
So tell them something you learned from this podcast to impress them,
Hopefully.
meet new people. If they're going to talk to you, it might be like
Who knows?
lifelong relationship because they are not going away.
Yes. So, guys, we reached the end of our conversation with Professor Mikhail Lemeshko. Thanks again for your time, and maybe we have you back for another episode.
Thank you very much. Yeah, definitely. I enjoyed it a lot. Thank you very much.
If you got interested in Misha's work, please make sure to follow him. Please subscribe to his YouTube channel, and you can find all the links in the description. And of course, if you enjoyed our conversation, please make sure to like. And if you want to see more episodes with future scientists or medical professionals, don't forget to follow me and subscribe. And Misha, I always have a slogan at the end of my podcast. Would like to know and be very honored if you agree to say the slogan with me together. Yeah?
What is it? Sure.
Let a little dose of honest science in your life and brighten up your day.
Let a little dose of science in your life and brighten up your day.
Honest science.
Let a little dose of honest science in your life and brighten up your day.
Yes, yeah, awesome. I could already take this now. Okay, so 1, 2, 3. Let a little dose of honest science.
Sorry. Sorry, I thought you recorded just me. Okay.
1, 2, 3. Let a little
dose
of honest
science
in your life and
brighten up your day.
Awesome. Thank you so much for your time. And we guys see us in the next podcast episode. Bye.
Daily dose of honest science.